In the chem activity number 20 and the corresponding videos, we're going to explore the quantum wave model of the atom. Now, as you know, we've recently been looking at the Bohr model of the atom, and you might be wondering, well, if we're moving to the quantum wave model of the atom, why do we bother learning about the Bohr model? One answer to this is to help us understand that science is a process. We're constantly revising our models, constantly trying to understand the nature of reality better. And one model leads to another, which leads to another. And so looking at these different models of the atom helps emphasize this. Another reason to have studied the Bohr model first and then to move to the quantum model is that the Bohr model is essentially a foundation to the quantum model. It helps us understand the quantum model. Now, as you may remember, Niels Bohr's model helped us understand that the energy within an atom is quantized. That is, there are discrete energy levels. This is the first time that we came to understand this. And of course, he came to these conclusions based on understanding the hydrogen emission spectrum, the fact that discrete energies of light are emitted by an excited state atom as it falls back down to ground state. So this helped him understand that indeed there are quantized or discrete energy levels inside the atom. Now, one of the drawbacks, however, of the Bohr model is that in spite of his beautiful equations and things, these could only be solved for the hydrogen atom. If you apply these equations to multi-electron atoms, which essentially means all the other atoms, the equations no longer worked. There must have been something else going on in the atom that, one, allowed the Bohr model to work for the hydrogen atom, but secondly, meant that we needed a more revised model to explain better what was going on in these multi-electron atoms. With that little bit of introduction, I'd like to introduce you to Erwin Schrödinger. But before we get to Erwin Schrödinger, first a little note about Louis de Broglie. Louis de Broglie was actually a French prince and a scientist, and in 1924 he was reflecting on the fact that if we could describe light as both a wave and a particle, in other words a photon, why can't we start to think of matter as having both wave-like and particle-like properties? So we know matter, definitely we think of it as being particles, it has mass. But then to think, well, maybe we can apply some wave equations to this matter. As it turns out, de Broglie was correct. Now, we all actually have wave-like nature, but when the mass is very large, the wave-like nature is actually essentially insignificant. However, for particles that are very tiny, like electrons and protons, their wave-like nature is actually quite significant, as it turns out. So now let's introduce our Erwin Schrödinger. So Schrödinger, a mathematician, and in 1926, he developed an equation to describe the electron as a wave. So Schrödinger was an expert in wave equations, if you will. And so he was a good person to be working on this issue. So he came up with an equation, and the equation, as you might not be too surprised, is called the Schrödinger equation. Now, as it turns out, the Schrödinger equation has many solutions. And at first that might seem kind of confusing. But then if you think of the equation that we've used to determine the change in energy in the atom, like the Bohr equation, that actually also has many solutions. In fact, it has an infinite number of solutions because it relies on the value n. And so we can calculate all these changes in energy as an electron falls from higher levels to lower levels or goes from lower levels to higher levels. And so it has an infinite number of solutions. So in the same way, the Schrödinger equation has many solutions. Each specific solution, and we refer to it as a specific wave function, and there's a symbol for it, psi, is called an orbital. And then one other comment at this stage. You may not be surprised that each wave function is associated with a particular energy, and that's consistent with what Bohr was talking about. Now, in some ways, it's a little unfortunate that each specific solution is called an orbital, because in part, the Bohr models seem to suggest that the electron behaves something like a planet orbiting the sun. And so when we see the word orbital, we might be thinking orbit. Yeah, so somehow there's this wave that orbits the nucleus. But in fact, that's not really what's meant by orbital. So a little bit of a sidetrack here. What is an orbital? Well, one thing to be clear is orbitals do not represent orbits. It's not a circular pathway around the nucleus. Okay, so just be clear, the electron's not moving in a circular orbit. Well, then how does the electron move in the atom? And one of the things to keep in mind is, remember we were talking about electrons moving from higher levels down to lower levels or falling, but we knew that that's actually not what's happening because we don't see the electron in between those different energy levels. So the movement by that electron, even in the Bohr model, is not understood. But in terms of the Schrdinger equation, here's the best answer. How does the electron move in the atom? We actually have no precise idea. And there's some interesting ideas about how we view an electron, and when we view an electron, we actually distort the electron or impact it by adding energy or changing its pathway. So for these really tiny particles, we really can't study them without interfering them. But then there's another issue as well. And that has to do with the fact that really we can only evaluate the probability of finding the electron a certain distance from the nucleus. Now that might sound a little strange because up until now, or at least in classical physics, much of the time was spent in a sense precisely defining where particles are and predicting where they would be after a certain amount of time. That was the role of classical physics, at least in part. But now we have Schrdinger saying, well, the best we can do is actually predict the probability of finding the electron a certain distance from the nucleus. There were a number of scientists at the time that were quite upset. You might recognize in this cartoon that this is one of the guys that was upset, Albert Einstein. And Albert Einstein famously was quoted in saying, God does not play dice. He really thought that there must be some workaround for the Schrdinger equation that we wouldn't have to rely on probabilities. Now, apparently at the time, Einstein and Niels Bohr were in communication. They would write to one another about the science that they're working on. And Niels Bohr is reputed to have rebuked Einstein's comment, God does not play dice, with, Albert, stop telling God what to do. And that essentially is the conclusion that scientists have to come to, in that the nature of the atom at the very tiny level is a very bizarre place and follows rules that are hard for our human brains to understand and certainly don't look like our macroscopic world. So let me tell you a little bit about the solutions to the Schrdinger equation. Now, in solving the Schrdinger equation, it is real math, and there are mathematical solutions, and I will show you some examples in a minute. But to make meaning to those mathematical solutions, we'd like to, in a sense, have a picture of what the solution means. Now, as it turns out, a wave function, actually, it's hard to understand what that wave function is representing. But we do know that the square of the wave function actually represents the probability of finding the electron a certain distance from the nucleus, and in a sense by some somewhat defined boundary. And these are often represented as electron probability density plots or boundary surface diagrams. If we want you to represent a solution to the Schrdinger equation, we'll usually ask you to draw a boundary surface diagram. Sometimes that's abbreviated as drawing an orbital, but technically that's not quite correct, because actually these boundary surface diagrams represent more closely the square of the wave function. So here are, as I say, three solutions represented by these probability density plots and boundary surface diagrams. And one of the things that you might be thinking about is that the 1s boundary surface diagram or electron probability density plot can be thought of as ground state. So I'd like to remind you that all of this is working with the hydrogen atom, and we're only talking about one electron and the probability of finding that one electron. So we can say that that one electron spends most of its time in ground state, and instead of simply saying n equal to 1, we're going to refer to that as the 1s orbital. Now, as it turns out, these orbitals, or boundary surface diagrams that represent the orbital, have defined shapes. And in this case, the shape is spherical. And you might think, for instance, of the 2s, the 3s, and there's a 4s, and each of those numbers that precede the s refer to the energy level. So it would be like saying energy level number 2, 3, 4. So you might think if the electron exists in these other orbitals, well, then we'd say the electron's in an excited state. So 2s is also an excited state. 3s would be a higher excited state. And you can see that these boundary surface diagrams and electron probability density plots, they have, in a sense, a greater volume. There's a greater chance of finding the electron further from the nucleus. So if we want you to represent an orbital, we ask you to draw a boundary surface diagram, which again represents the square of that orbital. And you can see a boundary surface diagram is in fact easier to draw because it has a defined boundary. And the idea is that it's within the surface that there's a 90% chance of finding the electron. And so it allows us to have a defined shape for that 90% chance of finding the electron. But perhaps you can see that the electron probability density plot would be maybe a more accurate way of representing this probability. So if you take the 1s, you've got the sphere, and then there's this kind of haziness in the outer edges. And it's the idea that as we move further and further from the nucleus, the chance of finding that electron gets less and less and less. And so eventually it'll just peter out to no chance. But you'll notice in the 2s and the 3s, and this would also be true for the 4s, 5s, 6s, these kind of look like bullseyes. But essentially what we have here in these regions where there's in a sense white or no blue, or no density, if you will, they represent the zero chance of finding the electron. And so we refer to these as nodes. Now again, this has to do with thinking of the electron as a wave. So if we thought of an electron as a particle, it would be really hard to understand these nodes. So there's a chance of finding the electron close to the nucleus, and then further from the nucleus, but no chance of finding it in between. And then you might, well, how did the electron get from close to the nucleus to further away from the nucleus? But if you think of the electron as a wave, and essentially it would be that point of zero amplitude that would serve as the node. And then there would be a crest and then zero amplitude, and then a crest and zero amplitude. So if we think of, again, the electron as a wave, these sorts of plots become more understandable. So again, in any kind of assignments, you'll only be asked to draw the boundary surface diagram or look at a boundary surface diagram. But please do keep in mind that it is more complex than that, because we have these nodes within the boundary surface diagrams, a more accurate representation of what's likely happening here. This simulation shows electron probability density plots for different orbitals. Here you can see a representation of the 1s orbital. You can see that this density plot shows a spherical orientation. I can also change the size so that we can, in a sense, get closer to the nucleus. But then when we're in the middle of the density representation, it's harder to see it. You, of course, will notice these particles moving all over the place. They're actually meant to represent the fourth quantum number, because within each orbital there are two different spins that the electron can have. We'll get to that topic later. But for now, I'd like you to imagine, especially because we're dealing with the hydrogen atom, that this sphere represents the probability of finding the electron a certain distance from the nucleus. And so you can see that little dot in the middle here is meant to represent the nucleus. And certainly as we get further and further from the nucleus, there's less and less of a chance of finding an electron. So this is what the 1s electron density plot would look like. Here is a simulation of the electron probability density plot for 2s. If we could compare it directly to the 1s, we'd see that indeed a 2s has a larger volume. There's a greater probability of finding an electron further from the nucleus compared to the 1s. In fact, you can see the nucleus found right in here, and so you can see indeed there's a lot more density found further away from that nucleus. There's also a node in this electron density plot. It's a little hard to pick out, but perhaps you can see kind of a faint circle within the circle, and that's meant to represent that region of space where there's zero chance of finding the electron. Here is a simulation representation of the electron probability density plot for a 3s orbital. If you look closely, in fact, there are 2 nodes within this representation, and if we could compare the electron density plot for this 3s compared to the 2s compared to the 1s, we'd see indeed this is a larger volume represented, and so there's a greater chance of finding the electron even further from the nucleus. There you can see the nucleus right there. And once again, I think you can probably make out the idea that there are indeed nodes within this electron probability density plot.